Hi, this is Amir from FinQuest Institute. In this video, we'll discuss the concept of regression and also implement a hands-on model for regression. This is one of the modules as a part of our certificate course on Python for quantitative analytics. So these are a few points which we'll discuss as a part of this video. So before we get on with the model implementation, it's important that we know the concept of regression. So by regression, we try to understand the relationship between two variables. So here we are focusing on linear regression. So let's say I have a certain generic equation as y equal to f of x. So the way to interpret this is y is a function of x. That is, y is my dependent variable and x is the independent variable. So the movements in variable x are going to impact the value of y. And through a regression equation, I try to understand this relationship in a better way. So there are different types of regressions which can be done. So you can have a simple linear regression. You can have a multiple linear regression. Then depending on the type of data, you may want to go in for a higher order equation, something like a polynomial regression. So in this video, we won't be getting into polynomial regression, but we'll focus on the linear regression bit. Now, when we say you're working on a regression model, that essentially means we are working on fitting the model to the available data. So there are a couple of ways to do that. So two popular techniques used by industry participants. One is ordinary least squares, or as we call it as OLS for short, and a maximum likelihood estimator, which we call as an MLE for short. So let's focus on the OLS technique. So I'll draw a simple scatter plot of data. So imagine that I have a certain set of data which is available, which I am plotting in a XY plane. And then I'm trying to fit the concept of regression on top of it. Now consider the diagram which I've shown on the right hand side. So these smaller red dots are what I call as the data points. So this is also an example of a scatter plot. Now I want to fit a linear regression. So when I say a linear regression, the point to note here is we are talking of a linear relationship. So when I say a linear relationship, it is just like a straight line relationship. So let's say I have something like y equal to ax plus b. So this is an example of a linear equation. Now why I call it as linear? Because the power of x, which is my independent variable, that is raised to 1. So whenever this is the case, we call it as a linear relationship. Whereas if you have something like a polynomial bit, then you'll have higher orders of x. So if I have maybe something like y equal to ax square plus bx plus c. So this is a quadratic equation, isn't it? And the power of my x has risen. So now the power of x is 2. So that implies that this is no more a linear relationship, that this is a polynomial relationship. Now in this video, we are going to focus on the linear relationship. This is what I have demonstrated via the diagram below. Now let's try to understand the concept of OLS with what we call as the line of best fit. So you see, I have drawn 3 lines here. So I'll just number them for convenience. Line 1, line 2, and line. I can have any such lines which I can plot through the data, because since I'm working on a model, it's completely my discretion as to how exactly I want to plot this linear relationship. So I can have n number of such lines. So for ease of representation, I have just shown 3 lines, but I can have infinite lines which I can draw through this scatter plot. However, out of all of these available lines, there is only one line which we call as the line of best fit. And this is what we are trying to figure out. So when I say the line of best fit, that means the number of error terms in, or the quantum of error terms in my model, they are low. So how do I decide which is the line of best fit? So this is where my concept of OLS gets used. So let's say I have a certain data point, let's say A, and let's say a certain data point B. And let's say the distance between the line and point A is plus 3 units. And let's say the distance between this line of best fit and point B is minus 3 units. So now we are talking of OLS. So the word to focus here is the squares bit. So when I'm fitting this line of best fit, I do not take the simple differences between or simple difference of the distance between these individual data points and the line. Why a simple difference is not the right way? Because there will be compensating errors which will happen. So imagine that I'm looking at points A and B. So I know that point A is 3 units away from the line of best fit and point B is 3 units below. So it's minus 3 units away from the line of best fit. So if I simply add up the differences, then these are going to cancel out. So when that happens, my model is going to get confused because the model will feel that points A and B are exactly on the same line. So I mean, it doesn't matter. But that isn't the case, isn't it? Because if we do that, the model fit is never going to happen. So that's why we use the concept of squaring of such distances. Because we know whenever we are squaring the distances, we are taking care of the negative terms which come into the calculation. Because as we know, plus 3 square is equal to 9 and minus 3 square is also equal to 9. So by using the concept of squaring, we are getting rid of the negative signs which are coming into the calculation. So that's why we are not allowing them to interfere or bring in any kind of compensating errors when we fit the model. So by calculating these kind of squared distances at each of these data points vis-a-vis the line of best fit, I come to this line number 3, which I call as the best fit line. So this is how I can fit a linear regression to a given set of data. So there are various applications to linear regression. So if I have to talk specifically maybe of a finance application, so let's say I want to forecast or I want to estimate the FX rates. Now I know FX rates can be a function of interest rate differential and maybe inflation differential. I'm just taking hypothetically this relationship. But this can be a relationship. That is, fx becomes my dependent variable and interest rate differential between two currencies and inflation differential between two currencies become my independent variables. So you could take any currency, say USD INR, Euro USD, etc. And using this, I may want to fit a linear regression model. So I can easily do that. So based on that, I'm going to get a certain model fit. That is, I'll get the values of coefficients. I'll get to see how goodness of fit of the model is using the concepts of R squared, adjusted R squared, etc. So that can be done in Excel as well. But here we demonstrate it through Python. So here we'll see that with the power of libraries which are available in Python, things become immensely easy. So before we get to the hands-on bit, just one small point which I would like to mention here. So let's say I have something like y equal to ax plus bx plus c. So let's say this is the regression equation which I have fit to the available data. So this is what I call the line of best fit. So when I say I am fitting the model to data, that means I am trying to find the best fit values for the model parameters, which I call as A, B and C. So these are also my model coefficients. So through the line of best fit, I try to calculate the best fit values for A, B and C respectively. And once these are calculated, then I can use these for any kind of further estimations which I want to do. So, so this is how a regression model works. Now let's try to do a simple hands-on application of linear regression using Python. So we'll build a model from scratch. For this, I have imported a sample database which we are going to use. So a sample file with 3 variables. So we have one dependent variable which I call as y and 2 independent variables which I call as x1 and x2. And through this, we are going to try and construct our own linear regression model. I will build my model on a Jupyter notebook. So I've just opened up a new Jupyter notebook and let's build our linear regression model. So let's say this is a model for linear regression. And here I'm going to use a library which we call as stats model. Now I'll import the required libraries. So these three libraries should suffice. We are going to use stats model because that has an implementation for linear regression, something which we are going to call in our model, and we are going to use it to calculate our line of best fit. So let me import the data first. Pandas read CSV. So a very handy library or a very handy property as a part of Pandas. The model which has been saved in my local drive. Now let's see if this data has been read by our Python interpreter. So before we go ahead, it's always good to test if the data has come in. So I just run this quickly to have a visual. So by this print statement, I am basically telling the interpreter to print the first 5 lines of this particular data set, just to see if Python is able to read the data correctly. Because so this can be like your first step in any model building exercise. Whenever you are importing any kind of data, it always makes sense to see if the interpreter is able to read the data. Otherwise, it may so happen that you work on that entire model and maybe there's some issue with the basic data reading. So that should not happen. We'll avoid that. So here you see that the first 5 rows of my data are being read. So that is fine. Now let's define our dependent and independent variables. So I have a small y. I'm using, so I've labeled my column as y inside my own, inside the same file which I'm using. Next, I'll also define the independent variables, which I refer to by x. And there are two variables which I'm using. So I have a x1. So again, these are the columns which I have named inside my file. Now we are going to be using stats models. So as a part of stats model, the first thing which we do before we fit the model, we need to have one constant term which we add, because as we know, for a regression we are going to have a certain intercept which will also be generated. So inside stats model, you require to add this constant in order to hold that intercept. So let's do that. X equal to sm dot add constant. Next, let's fit our model to the data. So I do OLS regression. I need to pass my parameters, which are my dependent and independent variables, dot. This is going to fit my model to the data. Next, I would like to do a prediction once my model has been fit. So I'll do OLS predict. Now this is going to give me a prediction. Now I can also have a nice summary table. So something which we commonly see in Excel as well. So if you run a simple linear regression inside Excel, so you go to data analytics, you select regression and you run the regression, it gives you a nice tabular output, which gives you the values like what are the coefficients, what are the relevant p-values, also what is the value of r squared, adjusted r squared, and other metrics, etc. So we can have something similar inside stats model as well. So we can have OLS reg summary equal to OLS reg dot summary, and I can print this. Just adding a few comments so that it becomes easy for us to track it later. So this is my dependent variable. These are my independent variables. I just added a constant fitting model to data, calculating summary statistics, and just displaying the result. So let's try to run this and see if we are getting the required result. Yes. So here if you see we are getting OLS regression results. We have these two terms. So x1 and x2 are, so the relevant coefficients for x1 and x2 are -27 and -10 respectively. And this is my intercept term. I also have the relevant p-values. So, and these are the other things. So, what are the AIC and BIC metrics? What is the R squared, adjusted R squared, F statistic, etc. Currently, I mean, we have a poor score for R squared. That is fine because we are using a hypothetical data set. So, whenever you work on real data sets, these are the two terms which also need to be concentrated on, R squared and adjusted R squared. Along with that, these p-values are something which need to be focused. Because currently, if you see, the p-values are pretty high. So generally for your industry applications, we are going to use a level of significance of 5%. So these are high values. So you may want to take care of the input data before you fit the model. But since we are using a hypothetical data set, and since our main aim is to see the implementation of a regression model, we haven't done those adjustments. But in practice, I advise that you do those adjustments before you fit the model to data. But this is one of the approaches of fitting your regression model. So there is another library in Python which supports linear regression. So that is also called as the scikit-learn or sklearn library. So primarily a machine learning library, but that also supports regression. So, so you'll get a similar result if you try and do it through sklearn as well. So that's the beauty of Python, and you can do one thing in multiple ways, and that gives a lot of flexibility to the developer. So this is a simple demo on implementing regression with Python. And this is one of the modules of our certificate course on Python for quantitative analytics. So in addition to this, there are multiple other modules which are very industry relevant, which we cover as a part of our certificate course. You can get to know more about our certificate course on our website, www.finquestinstitute.com. Thank you.